look at transformer variants. So it's absolutely necessary for today's class that you have the transformer architecture. Otherwise, you will probably not understand this class at all. But I guess we have the transformer, right? So the variants that we look at today are decoder-only transformers, then encoder-only transformers, and we will compare them a bit. But more importantly, the third part, more than comparison, I want to introduce to the Hugging Face platform today, which most of you have probably heard of or also visited. But I think it's important that we have a look at that as well. So let's see decoder only. So one thing that I wondered personally about was this question when Transformers came out, I was really not looking, not even at deep learning yet. I was already working on automatic machine learning, but not deep learning. I was really not interested at all in neural networks at that time. So in 2017, so I came really in late about this. But when I started learning about that, I really did not understand the idea of the transformer of using both encoder and decoder. Because what I thought was, like, if the decoder can process context, because in the decoder block, we use the context that we already generated. Right? So if we can do this, then why should we have an encoder altogether? I mean, what's the difference between encoding input and encoding output in the decoder part in two different blocks? Why? I mean, we could just say that everything that happened before is context, no matter whether it was input sequence or what we generated so far. Why make a difference between these two? Why not just have one block that happened before, now do something? And that was exactly the question they also asked. Okay, so if the decoder block needs to understand basically everything that happened before, and he does that in two steps: the self-attention block for the outputs, and then the second attention block that merges encoder and decoder state. And why make a fuss? I mean, why make it so complicated? Why not let's put everything, also the input, down there and just encode this as part of the decoder block? Yeah. So that would be the idea. You would say we just have some sequence, and then we codify these tokens in this context with self-attention, period. So this is exactly the idea of the decoder only block. So, okay, so in the decoder, then we generate a new output token, but that will be just added to the context. So one more token to be encoded in the decoder. Okay, turn up the slide here. Okay. So the standard transformer decoder block consists of the three layers. Sure. Yeah, we remember. Yeah. First, masked self-attention, only on the produced output so far. Then the second is the attention block, where we combine where we use that as a query, and we use the encoder output as keys and values. So here we combine encoder output and current state, and then we have the feed forward block. So which of the three seems superfluous here? Some. Which of these we could somehow throw out? So if the idea is to say that let's not treat the input sequence differently from what we have generated so far, but just everything is one context. So which of those would fly out of the equation? These are not. First one.
The second one, if we don't need the encoder, we don't need to merge encoders with the decoder status.
That's right. So if we don't have an encoder anymore, then we don't need to merge. Okay. And we just put everything that would be encoded by the encoder just into this part. Yeah. So this was done by Liud in 2018. That is a really interesting paper. So they dropped the encoder and they dropped the whole encoder part, and in the decoder block, they dropped also the second sublayer. Okay. And then what they say is, well, look, if we don't have an encoder, we basically halve the number of parameters we have to learn in this whole model. So it's dramatically more efficient in terms of parameters. Yeah? And before, the decoder block had 3 sublayers, but now it also has only 2. So I mean, so an interesting question is also, but wait, I mean, if we do this, then if we throw out this guy, then what's even the difference between an encoder block and this decoder block? There is a difference. But what's the difference? Because the encoder block also had self-attention and then the feed forward. Okay. So if we throw out this guy here, so that's one, what's then even the difference between the encoder block and what remains like this? In the other plane scheme. Okay. I leave it as an exercise to you. This question will pop up in detail. But I will answer the question in the course of the, but you should maybe come up, everybody for himself, with an idea. How is this block now different after removing this? How is this block yet different from the encoder block? And why is that important? So let's get back to the paper. So what they do here is a supervised learning test where they try to generate Wikipedia articles. So what they say is they downloaded millions of Wikipedia articles, and for each of the articles also related resources, documents. Probably what showed up in the references of the article, and they downloaded it. Okay, and then they said, let's make all these documents that we download. So let's say we have one Wikipedia article, and we have the documents that we downloaded. Let's say it's like 5 or 6 web pages that contain information about that subject. Okay, so these 5 or 6 web pages, all the content concatenated is part of this X. This is this X. And the Y is the Wikipedia article itself. Okay, so if we show these examples to the model, then he should learn what? He should learn to write the Wikipedia article based on the sources. Okay, so this is how we then generate text. Basically, the query is, but not the query, the attention terminology, but like the input is, look, I have these documents, generate me a Wikipedia article, but we have the true Wikipedia article as a reference. So we can compare it later. So he should write the article and then compare it with the ground truth. Okay. So I'm not going into details on how the loss function works exactly for this. It is not a word by word thing. Of course, we do not check whether the first word is the same as the first. That wouldn't make sense, because I mean, then you would get zero accuracy every time. But that's a technical detail. I heavily motivate you to read these papers. They are really, I mean, if you already know the idea roughly, it takes you like 20 minutes to read it. So as PhD students, it's not good practice to only consume slides and YouTube videos. It's really important to read the articles. Good. Now, that was 2018, June. In October, so half a year after the Transformer paper, in October, Radford and others, that were like only 4 authors on that paper, I think, and also Sutzkever. So Sutzkever was the 2014 guy with the LSTM encoder decoder idea. So he's also on this paper. They introduced the generative pre-trained model, GPT. At that time, GPT-1. And by the way, the acronym GPT was not even used in the paper. So GPT does not even occur. But the name of the paper is generative pre-trained model. So what did they do here? Basically, they took the same idea from Liu et al. So they took this. So I mean, I didn't say it explicitly, but so this idea here, yeah, throwing out the second one. No, I said it. So what they did was take the decoder only block, no encoder blocks, and in the decoder only. So we have to differentiate between decoder only architecture and decoder only block. But if you throw out the encoder, I mean, then this block doesn't, this sublayer doesn't make sense anymore. Okay, so in a decoder only architecture, you have a decoder only block. Right? The decoder only block means you have this block without the second sublayer. So this is what they did. And in GPT, they cite this paper and they use the same architecture. So it's really the same. What is the only change they make? The only change they make is how they train. This here is supervised learning standard. So they create a huge corpus of training samples, X and Y. And this is what they changed in GPT. Okay. So in GPT, they said, we don't have a Y anymore. We do not generate a Y. We just have text. And now what we do is that we create a sliding window of size K. And we say, this window goes over the text. And we take the K tokens, and the task is to predict the next token. Okay, so we also create supervised data, but it's a bit different because all the labels come just from the text itself. It's not like in the Wikipedia case where we have sources and then we have an explicit ground truth, which is the true Wikipedia article. But here we have just like one material, text, and then X and Y are inferred from this single material. Yeah? This is a very important difference. So here we create instances as vectors with the K tokens, and then Y is the next token. And then then we move the sliding window, and then and then we have the next word to predict based on what we have defined. So okay, so this is sliding window, and the loss function is simply the cross entropy loss. Yeah, sum cross entropy loss over everything. This is my X, this is my Y. So it's somehow really. I mean, really, where's the innovation? The innovation is, so they use the architecture from the decoder only from before. They use cross-entropy error. The only thing here is that they say, how do we design the training data? And I hope that the message that is clear now for everyone is that architecture is 20% of your success. 80% of your success is, what's my data generator? Because they don't even change the architecture, but who knows about this new article today? Who has heard about GPT? When all the innovation was this here, and actually quite straightforward. Okay, so they call this unsupervised learning because they say we start from the original data that is input to the whole procedure has no labels. It's just text. But this is super confusing. Okay, and I think this it's confusing and it's actually stupid. Okay, because unsupervised learning has been a fixed term in machine learning for 30 years or more, or 50 years. And now only because we do not have labels in the original input, it does not mean that it's unsupervised. Actually, it is still supervised, only that we generate the labels on the fly. Okay, so this was really bad naming, I would say, and a better name is if you say self-supervised learning. So it's true that you don't have labels in the beginning when you input your data into the algorithm, but unsupervised learning means that you have data points and try to understand structure in this. So this is what we use in clustering or in association rules and so on. And maybe, I mean, there is maybe one way of arguing why this could also be supervised, but the point is that the learning itself is still supervised. It's only that we generate, because we have labels here. We have a forward, we have a prediction, we compare a prediction to a true label that is supervised. So only that we generate these labels ourselves, and we don't need a labeling process outside anymore, which is of course the super nice. But let's not call it unsupervised learning. Okay. So this was one thing that GPT did. Now, what is very important to understand and maybe not obvious from the perspective of 2025 is that in 2018, nobody was thinking about something like ChatGPT. Nobody was thinking about that, let's generate text really in this way. So the objective here was not really text generation, but only text understanding. Okay, so the objective was not to create a query answer system really at that point of time, but they just wanted to say, we want a system that really understands natural language to then solve a standard task like classification. So sentiment analysis. I give you the text about like a rating of a movie, a text about how I like the movie, and then he should infer, did I like it, yes or no? Okay, it's very important. The task was not to generate text like ChatGPT does. The task was to understand text and then make a prediction. So this explains also the term pre-trained model, because actually all this logic here is not, this is not the actual task. For them, that was merely something like a preprocessor. So they did that, but then the actual model had also another, so there is a very nice figure that you can see when you open the paper, where they also have not only the, so they have a head to predict the next token, but also a head for classification that's only used at the end. Okay. So classification here, they have different tasks. So we have text classification, and then we have natural language inference, where we should predict some word in the middle, semantic similarity, multiple choice. So here, for example, they tell the system, okay, so they ask a question and give fixed options for answers, like multiple choice, obviously. Okay, so, and then he answers the question with A, B, or C, and is then judged based on whether his answer is correct. But that's a classification. So in none of these tasks, he must produce text. So in the paper, they have two phases. Training consists of two phases. In the first phase, they just train the GPT model in general to understand text, not to generate text, just to, it learns to predict the next token. And the only idea for that was to, not to generate answers, but just to create a model that understands what's happening actually. But then in the second part, which they call the fine tuning, Then they use concrete tasks where they want to use this model. And then they put a complete text, and the output is not so the input is a text and the output is not a text, but just yes or no, yeah? Good or bad, something like this. Okay. Good. So that was GPT-1. And then with GPT-2, the generative part became much more important, but the architecture changed. Okay. So other famous models after the GPT-1 were obviously GPT-2. GPT-2 was like, for most experts, the point where they say, wow, okay, this is becoming really a very strong system. So only in GPT-2, the generative aspect became important. And for most experts at that time, then GPT-2 was the real surprise. ChatGPT, not so much anymore, because GPT-2 already demonstrated very text generation abilities. Then we have Llama, that was, I think, also 2019, and Mistral from this French company. And there are some more, but essentially all of these are the same. Yeah. So all of these, and still, even the latest, well, I'm not sure about GPT-5, but at least until GPT-4, all of these are decoder-only systems. And the architecture didn't change. So the only thing that did change was how do we train this architecture, with which type of data and so on. So the idea was to make them, of course, and you saw that when you used GPT, that in the beginning it was only text, and we had also images and so on. So the architecture didn't change. The only thing that changed is that the input tokens became different, so that you could have not only text, but also images and so on. But in principle, the architecture has hardly changed. They changed some small aspects, but not conceptually, only for optimization. So attention, for example, Mistral has like a grouped attention mechanism, but it's not like that this is a conceptual change. It's just more efficient than the standard attention mechanism. Okay. So this idea of using decoder only is still state of the art today for these products. Okay.
When those models use the option of reason, even in that case, is the same architecture.
Reason?
Reason, yes.
Option of reason?
Yes.
Yeah, there is a reasoning option on reasoning.
Yes.
Oh, I have no clue. Don't ask me. I mean, this is a. So you mean when you use ChatGPT, you can tell him reason? No. Okay, no. No. I think that this is not related. So this reasoning thing, I think this is a logic that comes on top, that is not part of the decoder model itself. I mean, these systems don't think; they just produce next tokens. That's all. But you can then mount some additional logic on top, where you think, okay. So I mean, one thing is that some Altman always argued is that there is implicit reasoning going on. So they only predict the next token, but to do that, they somehow have a deep understanding that corresponds to thinking somehow. Yeah. That's a very difficult question to assess, because it's not clear how you want to measure this. You can think of reasoning as a process of thinking. You have an input and you have an output of the reasoning process. But this is not happening here, because you don't have a process, or the process is just like the forward pass. So where in the forward pass is the thinking? You could also define reasoning just as the ability to say something that you did not learn by something intelligent, something correct that you did not learn by heart. Because how would you? So if I ask you what's 13 times 12? Now you don't remember that, but you can compute it now. Okay. What is it? 156, I guess. So that would be reasoning. Now, if you say that this system basically only learned from a whole bunch of data, then it's not really doing inference. It's just a lookup table, a very efficient lookup table. But if that was true, then how could it answer you things that it did not ever look up? So you can easily create queries that it never saw, for sure. I mean, this is really easy to do. Okay, so I remember when I showed ChatGPT for the first time to my wife, I said, okay, what do you want to ask? And she said, okay, I want to ask it, when did the first dinosaurs that were able to play the drums occur? So, I mean, certainly it certainly had never seen any text about dinosaurs playing drums. Maybe in some children's books, or I don't know. But it came up with a very, very reasonable answer that wouldn't exist, and that, but one could think, I mean, so there seems to be some kind of very interesting ability of generalization in language, which could be interpreted as a kind of reasoning. I think there was also an example of some I never went into that, but I think there was an example where people said that ChatGPT learned a language or was able to communicate in a language for which it had never been trained. Yeah, but I'm not very sure about this. So, but this is not this reasoning option. So the reasoning option is that you mount a kind of meta logic that is about the model itself.
Basically, it's a feature of just wait. Produce some tokens, wait. Produce another token, wait. And combine those tokens and deliver final answer. You can see more of, I mean, perplexity, because you can be aware of the reasoning, but basically it's throwing tokens after tokens.
Yeah, but it's not a modification in the architecture of the network itself. I guess, at least not at this level.
Sorry, I have like a question, but what were the about like the especially the process of the development? I know that this is a French company, and I was like to build that they were like using something that was equivalent to like GPT-4 or 5. But in your opinion, do you think that this is possible for other countries and the small country or small developers to create something that could like easily like compete with these state-of-the-art models?
Yes.
So, like for example,
I mean, what would stop you? So, first of all, you need a lot of data, but that data is somehow now every time more ubiquitous. I mean, the crazy thing is that you can even use these models to generate data for you, right? So it's certainly possible. So one thing is the data, the other thing is the compute. So here we do not have the compute to do it, but I believe that we can get to much more efficient training procedures. So that almost, I believe that everybody could somehow train its own LLM from almost like from scratch, but it's not even necessary because, I mean, there are open models which you can adapt somehow. So using knowledge distillation techniques and so on, I'm pretty sure that, I mean, it's already being done. Okay, so I have colleagues also in the Netherlands, and just the guy who wrote me in Slack, he's working also on things like that. where they train new LLMs for specific topics. Yeah, it's absolutely possible.
Because for me, it was really impressive when I found out Mistral for the first time, because I got this idea of like all the Americans and Chinese I have, like the architecture and the capacity of building such a great technological endeavor. Then Mistral happened, and I knew that somebody in Chile, probably some relatives, began to the process of creating something similar. And I knew that I was working a couple of weeks ago in Zipaquirá, and they are building something called like having AI centers, maybe that in the Universidad. So I don't know if that's something like is achievable.
Yeah, I think it's absolutely achievable, but the point is, I think like only like 1 in 100,000 understand how to do this efficiently. So I think the limitation is not the resources in terms of the hardware resource, but the people resource. Because if you look at the architectures, also if you look at, I mean, if you look at, it's not, also if you look at, what's this Chinese thing? I always, DeepSeek. I mean, you see that you can do a lot of performance if you just have the right ideas. But the problem is that, you know, 99% of the people who use this don't understand the system, and they are not able to make any contribution. If you just use it, it's not developed. So this is where we hope we can make a difference. Okay, good. Next interesting question. By the way, if you just hold the question. What's the difference between that? Not yet. So so here's the connecting question that could give you a hint. So then Devlin, 1 year later, noticed so what happens in the decoder only block? We still have the mask, okay? So we have self-attention, but we still have the mask because we cannot self-attend to what happens in the future. So we have this teacher enforcing, and we have the full sequence that we should predict, but we then have to use the mask because we should not be able to look into the future, okay? Now, what they said was, what if my task is not generative? They noticed, look, they use GPT for non-generative tasks like text classification. So if I have text classification, then why should I look at the text that I have in this masked way? I could look at the full text immediately, not with this input padding mask, and not padding mask, sorry, with this mask. Yeah? So let's just take it out. Here's the answer. So if the only difference between the encoder block and the decoder only block is that in the self-attention, I have this mask. It's masked self-attention. And in the encoder block, I don't have the mask. So let's just remove the mask again. Because if I do not generate text, well, I can look into the future. I don't have to limit my. So when I'm looking at the first token, why should I prohibit access to the next token? The only reason to prohibit this is if I want to generate text, I should not be able or not be allowed to look at the next token, because that's what I have to predict. But if my task is not to predict the next token, but just look at the text and do a classification of the text, then why should I have this restriction? Totally unnecessary. Okay. So in general, it's saying if your task is, and this is now a bit recurrent because I already talked about this topic like 3 weeks ago. What was the difference between recurrent networks and I use a fully connected network somehow? And I said that fully connected networks can look into the future and recurrent networks not, because they only produce step by step. Okay, and that was nice if you want to prevent lookahead, for example, in time series forecasts. In time series forecasts, you want to forbid these lookaheads that you can look into the future. And then a recurrent network is nice because it forbids it naturally. Okay. But in some, depending on your use case, you can have lookaheads because it's not about generating the. I can have a time series, but my task is not to say what's the next values, but just is this a nice development or not, or what's in. Your answer is something else for which you can look at the full sequence. For imputation, for example, for imputation, I can look at the full sequence. Why not? Maybe, yeah. And here it's the same thing. So they are just saying, if you don't have a forecast task, then why forbid look into the future? And this is what the decoder block does. So the only difference between the decoder only block and the encoder block is that the decoder only block prevents look aheads into the future, and the encoder block does not prevent that. That's the only difference. So, a question, but now there is an interesting question, that is, if I only have an encoder block, then how should I train? How should I train an encoder only block if I have access to every token? So what's even the task I want to solve? And I mean, I could then do a task-specific training. I could say, okay, I give you the critics of a movie, and the final answer is yes, no. Okay, or like, was it a nice movie or not? But they wanted to come up with something smarter, similar to GPT, in the sense of GPT training had two phases. First, the domain agnostic phase, yeah, where you train to predict the next word, and then the second phase, fine-tuning for a specific task. And they here wanted to do something similar. They said, I want to have a training mechanism that is independent of a concrete task. Now, if I don't have a concrete task, then training GPT is natural because my training task is predict the next token. That made sense. So even if I don't have a concrete task, I can say, first, I want to have a model that predicts the next token. That makes sense. Okay. And in this case, the decoder only block makes sense because this is a generative task. Generate the next token. Right? Now, it cannot easily transfer this to the encoder scenario. Why not? Because if I now allow to look into the future, now where's the gap in predicting the next word? If I now can attend to everything, then where's the point in predicting the next word? Because I can just look it up. So, any idea what would you do to solve this problem? It's a very simple idea, actually.
You have access to every token, but you didn't have the order of the token, sorry?
Then you have the order. So you have, let's say, a sentence.
Mm-hmm.
So in GPT, training was, I give you the sentence and you have to, for every word, you have to generate the next word.
Mm-hmm.
And why was the task not trivial for the learner? Because we masked the upcoming tokens, so he could not see those. So that was why training was meaningful. Now, if we say that we take that away, that mask, and that was the only difference between the decoder only block and the encoder block. So if we take away the mask, where's the gag for the first position to predict this next token if I can already see the next token? Yeah, it's a problem.
For example, to translate language, you see all the tokens, but you need to, the output is a different language. It is not a problem if you can see all the circles.
Okay. That that's true, but then you already train for a specific task of translation. And we do not want to train for a specific task of translation, but just to create understanding for this language. So, what they said is, why not just say, we change the task. The task is not to predict the next token, but we just say, we take a sequence and we replace some of the tokens, some of the words with, like we censor it with black mask. So this word is basically taken out of the sentence. And now the task is to predict that word. But you have access to everything else.
That's not like.
No, but not a technical mask. It's just another token. So it's basically you introduce a new token that is like a paired token, but it's now a mask token. And
there is a blank that you need to.
yeah, there is a blank, but it's not part of the architecture. It's basically part of the data.
Yeah.
So we don't have a mask in the architecture anymore. So in the decoder, you have one sentence, and then for each sub-sentence, you have to predict the next word. And here you have one sentence, and you do only one prediction for the mask. Now that's the simplified version. In reality, that's not what's happening. In reality, they also do a prediction for every token, even the token that is available. So they just, for every token, they predict what's that token. The only point is that for the tokens that are not masked, so every token that is different from the mask token is not considered in the loss function. So you're not rewarded or punished for predicting. So you read the word bank and you say, oh, this token is bank. Or you say something else, doesn't matter. So if a token is not masked, then it will just not influence the loss function. So the loss function is only defined over the words that are masked in the input. And then the question is, does the model replace this token by the correct token? Okay. And that again is a simple what? A simple, I think they even use the mean square laws or something on the token presentation then. Or cross entropy could also be. So this yielded then what they call a bidirectional encoder representations from transformers or BERT, which is also a funny name because the encoder by definition is so this is completely redundant, okay? Because the encoder is always bidirectional. There is no direction. It's an attention mechanism. I attend to everything. So the reason why they have this here is that they wanted to say, and we take away the mask. Then you could say, which mask did they take away? The encoder doesn't have a mask. But that was a kind of response to the decoder-only architecture. So instead of saying, I only use the encoder block, they said, I take the decoder-only block and take away the mask. Then I'm bidirectional. But that's just the same as, say, I take the encoder right away, because that was the only thing that was different in these architectures, okay? So this is completely redundant here. So this does not have anything to do with, I was super confused by this, okay? Because I read something like a bidirectional recurrent network or so. But this does not have to do anything with bidirectional recurrent idea also. It's just like saying you can attend from both sides, but that's always the case in an encoder, so it's just redundant. Okay, so how does training now work in BERT? So in pre-training, and pre-training means I don't have a task specific, I don't have a specific task, or I create a general task. General task is to auto-complete words in my sentences, okay? So So they take, they have a prepared body, and 15% of the words were masked a priori. Okay, so in the first phase, they took all of the sentence and masked 15% of the words, and then they started training on that. So input would be something like this: the cat sat on the mask, and then this should. Then an output is being generated of the same length, and the loss function will only look at this here and ask what's the probability assigned to the correct token. That's all. Only thing, this is a bit simplified because we only have one mask, but actually you could have several masks in one sentence even. So not just one. So maybe you have had to complete several tokens in the, or to replace, not complete, to replace several tokens in the same sentence. Yeah. And this is actually this is a common example, but actually it's not a good example because after masks there is no word coming. But if there would be a word coming, then okay, here is a period token at least. But if there would be words coming, those could also be used to replace this mask. That's a very good alternative, and maybe even a better option to train a model that has text understanding than GPT. But after all, it's just two different use cases. Okay, so encoder only would be if you allow look-aheads, and decoder only is if you want to forbid look-aheads. It's basically the difference. Okay, now in BERT, they had two aspects in training. So one was the one I just explained with the masks. That was the, let's say, important one. And then there was a second one that for them it was equally important at that time, but we will just see in a bit that it turned out to be not that important. So the first one was this. Okay, let me go back quickly. So this is a name. Okay, mask language modeling, and mask obviously because we throw out some words that need to be replaced. So masked LM. When you heard the masked LM or MLM, this is this idea of you have to replace some words that have been masked. Okay, but the second idea they had for training was next sentence prediction. So what they felt was like to increase understanding, it's not only important to see which words belong together, but also to understand order of sentences. So every training instance consisted not only of one sentence, but of two sentences. Okay? So this is what they call a sequence in their paper. What they call a sequence is two sentences, A and B. And now what happened is that sentence B, in 50% of the cases, was a sentence that came after sentence A in the text corpus. So they have a huge text corpus, and they split it into the sentences, and then they create pairs A, B of sentences, some of which are really occur like this in the text document. First sentence A, next sentence B, and the other 50% of the examples are you have sentence A, and then you have something completely different, a random sentence. And why is that useful? Apparently, because what he should be able to see or to learn would be whether these two are related, so now there are two tasks simultaneously. So sentence A has some masks, and sentence B has some masks. And one of the tasks is to replace the masks by the correct words. But there is a second task. And the second task is we have a CLS token here, and we have two separate tokens. So these are just so that the model understands. It's a kind of helper for the model, which is not important for the loss function. It's only so that the model understands that here we have a separation between the sentences. And this means here starts a new task. Now, CLS stands for classification. And now the second task the model had was not only to replace the masks, but also to replace this symbol here with a with a token representation. And that token representation would be mapped into a linear layer and then a sigmoid function. So this is basically here, this guy should be replaced, or for this token, he should predict a representation that finally will give a binary classification. And what he should learn would be to predict for this token a new token that says true in the end, will say true if B is really a successor sentence of A, and false if not. This is a super smart idea. Because by doing this, then we ask the model not only to fill out the sentences, but also we check whether he is able to see whether that is naturally related to this or not. So the first thing is a kind of word level understanding. This is kind of sentence level understanding. Super smart. Right? Okay. Clear or not?
Are they trying to get a semantical relationship?
Yes.
Okay.
So, I mean, again, what is actually what is we have an encoder model. What is an encoder? An encoder takes a sequence and produces a sequence of the exact same length. It just changes for every token the representation. That's all. An encoder does nothing else, and a transform encoder does nothing else than changing the representation of each token. Now, here in these sentences, we have tokens for standard words. Those are not interesting for us. So if it says bank here, we don't care about bank. So we only care about the tokens that have a mask. For those, we know the token that should be there in reality. And what we want is that he replaces in this context the mask token with the correct token for this context. And we want that this token here is replaced by a token that if I put it into our already trained feed-forward network, that it will say yes or no in the end to tell us, I understood to create here a token representation for this guy that will indicate whether that came after A or not. I mean, whether the sentence in the original, that's like, I give you two sentences. The first sentence is, the coffee was hot. Second sentence, anyway, I enjoyed it a lot. Does sentence B come after sentence A? Yes, light, not necessarily, but lightly. Other example, the coffee was hot. Second sentence, I really came late to the office. Okay, so he should be able to say, in the first case, something, a token representation here that will be finally mapped into true. And for the second case, a token representation that will be finally mapped into false. Now, if you ask me, are we able here to train natural language models? Then the question is, do we have people who understand this kind of logic? Because it's not so much about coming up with new architectures. It's about being smart and how to train systems. And this was very smart. I think BERT, of all the papers that we discussed, the BERT paper is the most studied. I think the BERT paper is 150,000 citations. So that was really smart. Then next year, they came up with some modifications. So after BERT, we had Roberta, which is robustly optimized BERT. I don't remember what the A is. Basically, there is no innovation here in the architecture. Roberta has exactly the same model architecture than BERT. The only difference is that they trained it in a slightly different way. So So here is a table that is maybe a bit too small to read, but it's so you have it in the handout and have a nice overview of the difference. So if we compare BERT and Roberta, then the architecture is exactly the same. Only what they throw out in Roberta was the next sentence prediction. So what I just explained to you, because they found it to be not helpful. Interesting, right? Because it seemed really smart, but apparently it was not so necessary. So they only used the first idea of masked LM learning. They used much more training data, 10 times as much as for BERT. So that was already being trained on 16 gigabytes. I mean, you have to imagine these quantities. If we're only talking about text, 16 gigabytes of text. This is really a lot. So if you have a PDF file of a book without figures, of a book, let's say with 1,000 pages, that would barely be 1 megabyte. So 1 gigabyte are 1,000 megabytes. So if 1,000 pages of book are 1 megabyte, then 1 gigabyte of text are 1 million pages of books. So this is roughly 16 million book pages, more or less. And this is the 160 million book pages. So they just trained on a whole lot more data. Training duration, 1 million steps compared to, I don't know, actually. So much longer training here in this case to convergence. And I mean, look, okay. So here we have parameter count, but this is really just for, I mean, the architecture is really basically the same, but the question is a bit, I mean, how many layers do you have? Okay, so maybe this is for the models they published. This is where we're gonna get in a second. Because of course the question is, yeah, okay, you use encoder only, but how many of the encoder blocks do you use? In the transformer paper, they used 6. But as you see, this was then increased in BERT. Okay, so you can, and then depending on the number of layers or blocks you use, you get a different number of parameters. So that looks large, 340 million, but actually it's quite small. Because if you just think of the number of parameters you get, if you just have fully connected layers with many neurons, I mean, you get to millions very quickly. And other models, like specifically, I think GPT, I mean, there we're talking about billions of parameters. Okay? So they are relatively small. And then we have DistilBERT. I don't know how this is for you, because like in German, BERT is a kind of name, but it was a name for math, but like not being used the last 100 years, I guess. So it's these names are really funny, at least for a German person. I don't know how this is for you, but yeah. For me, it's always been funny. So what is DistilBERT? So in the machine learning, in the deep learning course, we talked about knowledge distillation. You remember? So I take a network and I create a smaller network, and then I use the first one as a teacher for the smaller one. Mm-hmm. So that is what they did with BERT, because that was relatively large. I said it's small compared to GPT models, but it's still relatively large. So they wanted to have something much smaller. Yeah. So here we have a comparison that is not even half of this size here, at least compared to the large model. Here it's approximately half of the size, 60% roughly.
Now they are accusing OpenAI of doing distillation with GPT-5, right? I'm wondering how can they test or prove that kind of things? How can you reverse that to say, hey, you use my model to train yours? How do you think they do that? Because there is a legal I mean, they are in the courts and lawyers and that kind of stuff.
I have no idea how you should be able to do that. Yeah, you can do a PhD about that maybe. Can you predict whether one model was distilled from another one? Idea whether you can do it or not. But I'm working with people in France right now, also on topics on distillation. And I mean, why do you do it? Why do you want to have smaller models? Because you want faster answers. So these models are so large, if you don't use a GPU, only doing one forward pass, one forward pass takes you 10 seconds. So now imagine how would the ChatGPT generation of tokens be if you, for every letter, you would have to wait 10 seconds. So this is the major achievement of DeepSeek, for example, that they have better inference times with simpler models. And this is also what happens in the Stillbird, not for text generation, but only for the encoder part, right? If you only have 6 layers, again, like in contrast to here, so you have only half the number of parameters. First, so the training process for this can be faster, but it doesn't. There's not much point in comparing that, because to train this, you need this already. So to be fair, you would have to add up the times. But then let's say the training time for adjusting your model here, the small one, that can be relatively fast. But the important point and the motivation for the research is that then you can have much faster forward passes, because you have, of course, if you have only 6 layers compared to 12, then your inference time is only 50%, because your forward pass is 2 times fast, or even 3 times as fast. Yeah. And interesting question, but I explained it in the last course, but not everybody was there. So you could ask, okay, but if this is so good, then why don't you train a 6-layer model right away from the beginning? Why do you have something so difficult in the first place? And the answer is that it's a bit mysterious, because in theory, yeah, you could do it, but in practice, it doesn't work. Because if you train this from the beginning and don't use this from scratch, and you don't use this knowledge, you converge to local optima that are not as good as the local optima you have if you use this additional knowledge. So it could be interesting for people who look into understanding processes with data from processes that could help you to build better models, so that your model converges to a better local optimum than if you train from scratch without having those data available. Good. Very nice. So let's sum up. Let's wrap up. So compare a bit encoder, decoder only, but in terms of BERT and GPT. Okay, so in the comparison is really encoder versus decoder. But here, I just, as a reminder, I use these names. See, okay, who are the 2 guys that we're talking about? Okay, so BERT is an encoder only, so there is no mask. No attention mask. And in GPT, we have the causal mask. Causal, it's not causal inference, of course. It's just causal means I cannot know what happens in the future. So I have the triangular attention, attention mask, right? Context access is left and right of the masked token in the case of the encoder, because actually there is no restriction. Okay, I don't have a mask, but the mask makes here that I only have access to the left. Then the training objective is the MLM, masked language modeling, or in the original case of BERT, we also have the next sentence prediction. Binary classification is B after A or not, but this is not necessarily the case. And here the task is next token prediction. This is really the important difference. The question is not really, GPT is not a technology. Any one of us could implement this or this in a homework exercise. What you cannot do in a homework exercise is train with so much data. But the innovation is really somehow trivial. And it's not like those companies have those models because the people are so much smarter. They are very smart, by the way, but because they have like the hardware resources and also access to the data to train all that stuff. But nowadays, you have access. Everybody of us has access to a lot of data. I mean, if you just think of how many PDFs you have on your laptop, books, just with this, you could already train both of these models. Very, very solid way. Only that then it's more a hardware problem. Yeah. Yeah. Okay. And the training style is then, of course, as well related to this architecture. So here again, I do everything like, okay, in both cases, I do everything simultaneously, but here, because I don't have the restriction, it's really I'm just interested in the parts of the input where I have the masks. And here I basically simulate the autoregressive behavior. I'm doing it in parallel during training because I have access to the ground truth. But what I do is I simulate the autoregressive behavior, and here I don't do it. Okay. Okay. Very good. So one takeaway is that this is the last line here somehow. So if you look at the use cases, then you see a use case for GPT is a generation, completion, and chat. So everything that is ChatGPT today. And that is precisely what they did not do in the first GPT paper, because they had exactly what is the use case of BERT. They had the objective in the GPT paper was understanding and classification. Okay, so all of this is a bit weird, but of course now in the retrospective, one can understand this maybe a bit better. And what one could somehow say, GPT-1 was a bit like GPT-1 was a bit misplaced. Actually, GPT-1 was solving these use cases, and it should have been done with an encoder. And they said, let's do it with an encoder. But then, starting from GPT-2, then they started to concentrate on the use cases for which the decoder actually makes sense. Decoder only makes sense, which is the generation part. Because in the generation part, you don't have a look at it. So roughly say decoder only is for forecasting tasks, produce something, and encoder only is for a task where you don't want to produce something. You have a complicated object and then you want to classify it, for example. Yeah, you want to say something about that object.
I guess we can use it for knowledge representation, right?
Just like social listening, for example.
Yeah, the point is, both have knowledge representations. It's precisely where the confusion comes from. Yeah? Both have knowledge representation. The only question is whether for your knowledge representation, you have something sequential. Is there something that tells you should not be able to look into the future inside your sequence? So in your sequence, you have an object here, and what is relevant about this object should not have access to the rest. Is this the case? Yes or no? If yes, then you want a decoder. If no, if you can look at everything, then an encoder is fine.
Seems like I need, if I want to use knowledge representation for machine-to-machine tasks, and I want to give this to another neural network, I want to use an encoder. But maybe if I want this to be interpretable, I would like to use a decoder because I want to use a specific representation in the chat form.
I'm not sure whether interpretability is a relevant keyword, but but after all, it's very simple. It's really only this question of look ahead into the future, allowed, yes or no. If a look ahead from one token into the future is allowed, the encoder, if it's not allowed, because there is something like a construction task, a forecast, a production task, then a decoder.
Could say that in simple terms, encoder is what you use when you have to give some
something from a machine to another machine, but GPT is when you have to deal with flash.
I don't really understand this machine to machine argument. I mean, I think it's not relevant whether it's machine to machine. You can have machine to machine in both cases. The only question is whether you produce something or not. And in general, a decoder, because of this, a decoder is a bit more powerful because he can do everything that he can do as well. But this more powerfulness comes at a price. And the price is that you do not use everything that is available, maybe.
Mm-hmm. Mm-hmm.
Because of the mass.
Yeah, because of the mass.
Yeah, because so if for some reason we try to use GPT and just okay, no.
What is the question already complete, or?
You could say that. No, I was asking like if you could take the GPT and re-include the attention layer.
But why would you do this?
Yeah, that's the answer.
This is precisely the point to understand here. Understand your use case, and that will tell you which of the two is better. So don't use GPT. Actually, it's very disadvantageous to use GPT for tasks where you have look ahead a lot. So, I mean, look at this. So here, I give you a task. So let's do time series forecast.
Yes.
So please tell me, how does the curve go on? No, sorry.
It does.
Following a value of the line.
Yeah. So how does the curve now continue after this? That's now we're in the decoder setup. Okay. So in the decoder setup, please tell me what happens now.
Well, I think that that's going to keep still and then it's going to fall down, I guess. But I think that that's something that the GPT would say.
So the decoder has now, he can only use this, okay? So the decoder could now maybe say something like this. Whatever else, I don't know. So, okay? But now what I tell you is actually the task I give you is not, actually I'm not in a forecast set. Okay, actually I just had a master's student who had the task doing imputation in time series. Yes. Yep. So if you have imputation, that means you have missing values. Okay, so we already know that that after we see this, afterwards we see this. Now, please tell me whether this information is useful or not for imputation.
It's not useful, and that's why you're going to use birth.
It's not useful. So you know, sorry, but you made two mistakes in one sentence. You said it's not useful, which is wrong because it's super useful. Because if I know already that I continue this way,
For imputation, prediction is bad.
I know I should complete it this way somehow. And the second is, even if you say it's not useful, then you say, okay, if it's not useful anyway, then I don't need this information. I can have the mask, and then a decoder is good. But the point is that it is useful. I should have access to this, and then, but the decoder doesn't make use of it. So here I should have a bird. Well, not a bird, because I mean, this is not text, but in this case, I want access to everything. So it's very good to think of examples like this that are not text related to understand the difference between encoder and decoder, because essentially it's just, do I have look ahead or not?
Okay. So it means that if we are going to do imputation, we do not need to look ahead.
We actually,
Because we need to look ahead for forecasting.
that's
What?
Well, if you're using GPT or BERT, you are not gonna impute anything at all. Because that's what you use when you.
No, but I'm talking about the time series example.
Yeah.
Because what I understand, the symbol between those is that when you are going to do embeddings is in text is the equivalent of doing imputation in forecasting. In that case, you do not need what is going to go after, because that's that's enough because what you have is enough. When you're going to do forecasting, you use decoder, you use GPT, because you need to know what is going to go next, because that's the way that you train the model. Because if you do not know what is going to happen, what truly happened after a certain point, you are not able to do prediction and to know if your prediction is wrong. Okay, I'm confused.
In the decoder, I should predict what is going to happen in the next step, but I have to do that without knowing what will happen after that.
Okay.
In the encoder, I also have to fill up something, but it's not in the context of the task that I have to create a sequence and this is my next token, but in general, it's not just like, think of it like imputation. Somewhere I have a missing value, but I am allowed to know what happened after that.
Because it doesn't matter. It's not going to break the training process.
It's not part of the justification of the method. It's just like to say in some problems you can have access to what happens after, and in some you cannot. This is not like what is better or not. This comes from the domain. So if your task is to do imputation, then you typically can look at what happens after. Because it's only about, I mean, it's no data leakage in this sense. But if your task is to do a forecast, then looking into the future is like cheating, and then it's forbidden. So this question or this criterion, look ahead, allows or not, this is not something that you decide. It's something that is a property of your problem.
You do not have to stay in the ladder. You just use it or not use it of the task.
So the problem tells you, is a look ahead allowed or not? It's no decision. It's just a property of the problem. And if a look ahead is allowed, well, then goddamn, you should use the data from the future because that is a big advantage. And this is exactly what the encoder does. And if it's not allowed, then you're not allowed to use an encoder, but then you can still use a decoder.
Okay, understood.
Very good.
I have a silly question. There are some models that combine the benefits of what? So, you know, because Bert is good because he used all the data, right? In the future.
BERT is good for imputation.
And for embeddings, right?
And embedding comes before. Embedding is context free. BERT is good for contextual embeddings, if you want to put it like that.
And GPT is better for generate.
Correct.
So if it's possible to combine these two words.
Of course, if you have but the question is, do you have a problem where you don't want to have those? Probably not, because it's a bit binary. Do we have look ahead loud? Yes or no? This is a bit binary. So probably no point in having both. So that being said, there are three different types of transformer blocks. We have the transformer block that we saw. We have the encoder block, which is standard that we saw last time. And the standard, I'm just noticing that I also wanted to talk about vision transformers. Oh, I need another class for that, I guess. Let's see. So we have the standard encoder block and we have the standard decoder blocks. These are the two blocks we saw last week in the original transformer, okay? And the BERT, so here we also have the original transformer and BERT uses only this. And now we learned a new block type, which is the decoder only block, which is used in GPT, Llama, and Mistral. This is the same block as this without the second sub-layer that connects encoder output with the current decoder state. So that's mainly the difference. And yeah, so here we have the masking. In both, we have the masking. And the difference between these two is just that we don't have the second block, but the second block anyway doesn't have this causal mask anymore because the mask is already applied before. Yeah. Okay, so this as a kind of summary. Now, okay, so here are the references. So you're super invited to look at those. They are very, I think, based on the class, they should be really easy to understand. Now, let's look a bit at this Hugging Face platform. So, so this is super silly. I don't know who came up with this silly name of Hugging Face, but okay. So basically, this is a platform where people can share transformer models. In general, somehow these learning models, but it's mainly transformer models. So it's a website, but it also comes with a Python package. So the Python package is not called Hugging Face, but the Python package is called Transformer. So if you do pip install transformer, then you get basically the API of the Hugging Face platform. Yeah. Now but the cool thing about the platform is that they give you a user interface to play around with the architecture. So we could look, for example, at here. Let's look at the models they have, which are quite a lot. So you see here for which tasks they are. For example, text generation. There are 42 more tasks that we don't have here. So look at all of this on the left side. So all of this are different tasks. Okay. So texts. Sorry. Text generation. Which kind of model should we find here? The GPTs. Thanks. So here, okay. So here we have the GPT model. There are two actually, GPT OSS and Safeguard. So let's look at this, for example, GPT. Okay, 4.7 million downloads last month. An interesting statistic. Now, what is cool here is now that, okay, so we have a description by the authors, which is OpenAI. Someone has heard of it. So where you see, okay, they have two different models, one with 20 billion parameters, one with 120 billion. I mean, imagine this number, 120 billion parameters. So if you download this model here, this I think it's like 14 gigabytes. 14 gigabytes in weights.
You actually need a GPU of
80 gigabytes. 80. For the big one, you need an 80 gigabyte GPU. Yeah. Here it says that also. Yeah. So it's been insane. Now, what I wanted to show you is you can play around with this guy here. So here, this will not be so super instructive, but you can say who is the president of Bangladesh. Now, we can ask this ChatGPT, but the gag of this website is that you know exactly which model produces you the output, and you can download the model. Okay. So this here is the output of this model that you can download and use on your machine. Okay. So the gag here of using this is not that you use it like ChatGPT, but that you understand what can the model do. Let's see what this model knows me. Actually, I didn't. Okay, it's German actor. Hey, this guy is even on Christmas. This guy's even younger than me. That's humiliating. Okay. So that's GPT. Let's look at BERT.
Sorry, Felix. It means that if you are going to use this, you have to run it in your computer, but not run it into a. When you're
I mean, of course, you. For me, this, by the way, for me, this is the interesting use case.
Mhm.
I think on-premise is getting back.
It's getting what? Sorry.
It's getting back because of security concerns. The problem is that now you say, so everybody went to the cloud. That was already something that I didn't understand very well because almost for everybody, cloud is more expensive than having your own stuff. Yeah. So why does everybody go to the cloud? Because there are people who are in charge who make decisions, and those people don't want to be responsible. So they say it's not my money, but I don't want to be responsible for anything. So in the moment where I tell someone else to do the job, then it's for security breaches, for whatever happens.
Yeah, I can blame
Okay.
you on it.
So cloud computing was, I mean, it's super important, but personally, I don't understand. So I think I understand that it's easier. And you have uptime guaranteed. You just say buy and deploy, and you don't have all this. You don't have like the setup costs in the sense of not so monetary, but you need someone who sets up everything, who's responsible for the infrastructure. So you get rid of all of this, and this is super expensively paid. Yeah. So for me, cloud is an enormous business for those who run these platforms, but it's somehow a bad business for everybody else. Why does it work then? Because people who are in charge don't want to have this overhead. Where does cloud make sense? Storage. Yeah, that's so cheap. That's good business for everyone.
When you want to back your application with, for example, I have a CRM, I want to make it smaller, I want the CRM to access an agent and that's not. You have your CRM deployed on AWS, you need to deploy your agent on AWS.
Okay. Now, what happens with the LLMs? With the LLMs, now people start to share all sorts of confidential data with these LLMs. They go directly to the cloud and are shared with the AWS, for example, and that's I mean, it's completely scandalous, and basically you give away all your business secrets, and also data from third parties, which you are actually not allowed to share with Amazon. So there is two solutions to this. One is that you have your own LLMs, which would be much cheaper, and you would solve this problem of confidentiality. And the other solution is that there is a new structured contract that will make sure that they will not look at your data in the LLMs. But it's, oh my goodness, I mean, how would you even do that? Okay, so how do you use an LLM without looking into the data that they? Yeah. So it's so I think that makes on-premise get back on stage again, because it's a bit more work to do, but anyway, it's much cheaper, and you don't have this privacy. So let's look at Bird. Bird has some more downloads than GPT. 55 million downloads last month. Yeah. So you see that Bird is actually much more popular among developers than GPT. So GPT is what everybody uses at user level. Bird is what everybody uses at developer. Now it's less compute power. And here, I mean, okay, this is the base model, and this is here super nice because now you can play around with this. So. So what should we fill in here? What would you put? Maybe or something. So let's see what he puts in. But look, these are probabilities, okay? So it's 12% probability. So he's really very, very unsure about all of this. Okay. It's very nice, okay? But now, now let's give him more context. We now want to have the same token here, but we give him more context. Specifically the scene with the car brakes. Now, what should be the mass?
Of course, it would be
Okay.
being.
Yeah, but Obi has a 25% also, so. Sorry, that was. Oh, look, I'm not even sure whether that is. Okay, look, okay, the question mark really made the difference. The question
Which is like it's like you're asking yourself.
Yeah, because that seems like you are asking, do I like this?
Yeah, exactly. So you now see the difference between an embedding and the encoding. I'm embedding the same thing twice, but encoding makes that I. Let's ask him to also fill up this here. Okay, he can do this here. So in the interface, you can only have one mask apparently, but okay. But here, the important thing about this here is to understand this is not what is BERT for. This is only a playground. What is BERT used for? He will take your, it will take your whole sentence, and usually you won't have a mask. This is just like to see how training or how he works for the task on which it was trained. But this is not how you use BERT. So this is BERT training and BERT in usages. I give you the sentence, and for every token, I get a new representation. There is no mask anymore when I use BERT. Just give me. So the key is. Or here I could put a thing, maybe, at this thing very much. So if I would not have this context, then thing would have some, okay, now he doesn't have a mask, but so I don't see the embedding back, the encoding vectors here, but those are that I'm really interested in after all, okay? So this is where this is not so cool, this website, but this is why you can download it and play at home. Because here you see how it works then. So you have the package from the transformers, you use the pipeline, and okay, they are also masking here, but it's really not so important. You can just put in the sentence you have without any masks, and you will get a token for each, or a representation for every input token you put into this. Okay, so or I'm right now I'm not even sure whether you get the logits over all the possible tokens, or it should be like that. Probably it should be tokens. Probably just over the tokens. Okay, so this is really the use case that you get numerical representations of every word, and now the important point is that he knows the context, and if you add something, then the vector you get back for this token will change because of the context. This is what makes it different from the embedding, which is context free. Okay, so very good. This is then maybe hopefully part of your new playground. We learned a lot again today, and we didn't even solve vision transformers. Questions?
If I have a training model, the training model I can't update. I mean, if I train model related with I don't know, purpose related with maze, and we have a new research, and I want to upgrade model, I can make a patch, or I need to train from scratch?
No, of course not. You will, of course, just take the model and update it with the new data. So in general, there are two ways how you can, let's say, incorporate new knowledge. The first one is that you take your new knowledge and somehow retrain, and the other is that you just use that as part of your context and you don't retrain anything, which is often done today because then you don't have to retrain anything.
And create a new one. And create a new version.
No,
But not.
no.
So
You just say. So maybe you have some kind of conversation with the model, and you just say, I pretend that before the conversation there was another conversation, and in this conversation you just put the whole knowledge that you have in natural language, what you can do. That didn't work so well before because you have limited token lengths, only like something like 10,000 or so. So this is why people came up with RAG, retrieve augmented generation. I think it's every time less important because you can just now put the knowledge into the prompt. But of course, some things you need to look up. So I mean, RAG remains relevant, but all of these architectural things are without retraining anything. You just take network as is, and what you have in addition, you just use in the context. The other thing is that you update your model. But then, yeah, this is computationally very expensive. It's a matter of speed, because the more knowledge you, so like putting things into the prompt, just in natural language, this is convenient for you as well, because you just say, I already know this. Now, your model has to attend to all that. And that makes the inference much smaller, much slower. So if you do this, then maybe creating the responses will become really, really slow after time. You will not notice if you reduce cloud services because they will just scale up and charge you more. But if you do it on your own machine, you will see like, I mean, it's clear. If you have to attend to nothing, because just say you start the conversation from scratch, then it's super fast. If you have to attend to 20 books, then only computing all these attention weights already takes you 20 seconds or so. And then, yeah. Ok. Muy bien. Chicos, que descansen. Gracias. Igualmente. Gracias.
Así es.
¿Qué se llama? ¿Qué dije? Ahora recuerdo. Se llama Martín o Martín.
Es la
La receta.
Manuel, te revisé finalmente con Alison.
Sí, es corregir el equipo porque yo no como dije, pues tenemos el que más o menos. De hecho, se acaba. No es no es ¿cómo vas a hacer lo que vemos es en realidad lo que se pone aunque definitivamente ese problema. Eso hay que conocer. Y que no ha sido hecho y no es trivial. Entonces, demostrar a la vez que es interesante que no es trivial y hay trabajos relacionados anteriores, pero todavía porque algo que es. De los 8 que tenemos, uno lo ha logrado bien hasta ahora. Considero por dentro. Hay una, o sea, no, pero eso hay un formato de recomendación que van a recibir de todos, o sea, todos van a leer de que les y van a hacer entonces, la prueba, que no la he visto, ¿cómo? Sí, no la he visto. O sea, si quieres, vería, iría de repente. Hola.
Profe, le queremos dar una tontería.
Mostrar
Mostrar una tontería.
no, tonterías, mostrar.
Ok, bueno, no simplemente he estado haciendo un embedding un poco interesante. Entonces, le quería explicar pero unos datos de la clínica para predecir dónde, bueno, para decir dónde pueden estar la clínica. La lista de 45 pacientes con direcciones. Yo, Paulín, tengo la temperatura. Pero mi dirección. Entonces, lo que yo hice para intentar añadirle más información para de la persona, pues buscar un mapa catastral de las sabanas y decir, viene una zona que es estado 1, 2, 3, 4, 5, viene una región residencial, no residencial, busque qué tan lejos se demora la clínica y según la distancia en carretera desde el lugar hasta la clínica. Y después lo que yo dije, bueno, voy a hacer una posición pero me di cuenta que tenía la clase de área, la clase de categorías, y se me funcionó muy bien.
Bueno, mensajes usaste con éxito.
Pero cuando el rey funciona. Y otro Dios que utilizo pero el mapa de Euclides entonces dije sí, con la métrica de lo que utilicé y el R cuadrado me dio un país. Pero lo que pasó fue que yo voy a agarrar el error y voy a tomarlo como una forma de medir un particular, hay potencial o está vinculado. Lo que yo hice fue agarrar toda la información que era y la hexagonalicé. Entonces, si en un hexágono hay 15 personas, entonces hay una variable que es el número de personas y una variable que es el número de personas. Si resulta que ahí está atravesado un polígono y el 50% de ese territorio corresponde a un polígono residencial, entonces es un polígono que está tocado. Y si la gente, la mayoría de la gente que está ahí está en cuenta por una distancia de 15 minutos, entonces la distancia de ese hexágono es de 3 minutos. También ahora lo que estoy pensando es, no sé muy bien, depende cómo hago para meter las características de que un hexágono que se trata de un hexágono son estas características. Entonces, o sea, yo hice una solución que fue simplemente con entonces, hacer como el equivalente a un pool. Si es cada hexágono tiene su valor, actualizado, que es el promedio de los otros hexágonos alrededor. pero pues eso no es una solución para metodología en cualquier vida. No sé cómo hago para realizar la estructura. O sea,
Ahí empecé
tres capas tensas como de 64, pero no sé cómo
cierto. Es decir, siempre intentar por ahí una casa y luego como o sea, sería como clasificar municipios. Tendré que hacer no puedo hacer ahora y estos tienen este otro comportamiento. ¿Sí? O sea, como así.
Entonces, ahí tú tienes tú eres el valor agregado. Y tú encuentras eso, pero no te ahora sí, no te pones. Y no te pones como solo antes. Tocaría sentarme ahí un par de horas también, habiendo con las calmas, pero sí, pues esa y el otro pero si queremos entonces también la visualización que puede ser de ecuación porque es para